In this video, we'll discuss the framework that allows for the control of error rates in decisions arising from hypothesis testing. First, recall the procedure that we go through when testing scientific hypotheses with data. We first state the competing hypotheses being compared. These are statements about the true population value of the quantity of interest. In the context of regression models, the null hypothesis, H0, states that the true population value of the coefficient of interest, beta, not beta hat, is 0. That is, no real effect of the predictor variable in the broader population. The alternative hypothesis states the opposite, that the true population coefficient is non-zero. This is the two-sided alternative, which should be used in situations where we don't know the true sign of the coefficient. Arguably, in most settings, we are not completely sure of the sign. We start by assuming that the null is true and use our data to quantify any discrepancy with the null hypothesis by constructing a test statistic. This test statistic measures how far the coefficient estimate is from the null value, the value proposed for the true coefficient in the null hypothesis, which here is 0. If this test statistic is large in magnitude, then this suggests large discrepancy with the null, and we would favor rejecting it. Another way to view this is that if we look at the sampling distribution of test statistics under the null, that is, if the null were true, a large test statistic would be rather unlikely because it's far from typical test statistics arising if the null were true. So maybe the premise that the null is true is actually wrong. Because thresholds for determining whether test statistics are large enough vary from situation to situation, we look at areas underneath the sampling distribution as a calibrated measure. Specifically, we look at areas beyond, more extreme than, our observed test statistic. If the test statistic is large, this area will be small. For the two-sided alternative, we look at a two-sided area because we are considering estimates of both signs. This two-sided area is called a two-sided p-value, and when the p-value is lower than a predetermined significance level, alpha, we reject the null, concluding that we have evidence for a non-zero broader population effect. Otherwise, we fail to reject the null, concluding that there's not evidence to say that there is a non-zero broader population effect. It turns out that when we reject the null, when the p-value is less than the significance level, we are actually controlling the probability of making a certain type of error. That error is an incorrect rejection of the null hypothesis when in fact it's true, and it's called a type 1 error. When we use a significance threshold of 0.05, we are controlling the probability of making a type 1 error at 5%. That is, the probability of rejecting the null hypothesis incorrectly when the null is actually true is 5%. If the null is really true, we expect that only 5% of samples will give us data that lead us to incorrectly reject the null hypothesis. So why is this? Say, for example, that the distribution of test statistics under the null follows a standard normal distribution. That is a normal distribution with mean 0 and standard deviation 1. Using the 68, 95, 99.7 rule, we know that 95% of samples will give test statistics between approximately -2 and 2. This means that 5% of samples will give test statistics that are larger than 2 in magnitude. In other words, the p-value being less than 0.05 is exactly when test statistics are larger than 2 in magnitude. If the null hypothesis is true, and we obtain a test statistic greater than 2 in magnitude, we're going to reject the null because the p-value will be less than 0.05, and this will be an incorrect rejection because the null is true. So how often will this error happen? 5% of the time by definition, because if the null is true, 5% of samples will generate test statistics larger than 2 in magnitude. Okay, so this discussion motivated the type 1 error rate. There's actually another important error rate in hypothesis testing. To organize information about errors, it'll be helpful to use this table of different outcomes, where the columns correspond to the truth about the null and alternative hypotheses, and the rows correspond to our decision from hypothesis testing. So, as we just discussed, when the null is true, but we reject it, this is a type 1 error. And we control the probability of this at alpha, our significance level. Contextually, this means that there really is no effect or relationship in the broader population, but we claim that there is. If we fail to reject the null when it is in fact true, this is a correct decision. The probability of this occurring is 1 minus alpha. When the alternative hypothesis is true, but we fail to reject the null, this is called a type 2 error. In this type of error, there really is an effect or a relationship in the broader population, but we fail to detect it. The probability of a type 2 error is usually denoted beta, not to be confused with our regression coefficients, though. The opposite of a type 2 error is correctly rejecting the null when the alternative is true. The probability of this correct decision actually has a special name. This is called power. It turns out that there are different factors that affect power. We'll discuss these in class, but knowledge about these factors can help with study design and planning. That is, we can plan our studies to increase power and decrease the probability of a type 2 error.